We would like to go to this listen to Agonagic's talk about lectures. But okay, so let me actually say something. So we have this threefold. Here is what we would like to do today. So for today, we are interested in a fourfold, Calabi-Yau, preferably fourfold, inside which there is a divisor sitting. So Y is a divisor whose normal bundle inside X is negative. So we would like to study this thing. And we would like to questions. Question is, when can dt theory of X4 be equal to dt theory of Y? So this is what we would like to do, because we don't want to go through this fancy machinery of derived algebraic geometry. We would like to just do regular algebraic geometry, and in some cases, the invariance of a fourfold can be equal to the invariance of the threefold that sit inside the fourfold. Okay, so that's what we would like to do. So, but I would, in general, I would do a setup. So here is an example. So let Y be a smooth quasi-projective variety of dimension in general D. Now let's put this dimension D minus 1. Let X be the total space of the canonical bundle of Y over Y. So this is an example. Okay, canonical bundle of Y over Y, and let I from Y into X be the zero section embedding. Okay, so we have this situation. Let M be the moduli space of compactly supported coherent sheaves F in coherent abelian category of compactly supported coherent sheaves on X with fixed Chern character, for instance. Okay, compactly supported. I need to tell you where they are supported, whose scheme theoretic support is Y. Okay. Well, the scheme theoretic support is Y. So they have no thickenings outside of the Y. Okay. Okay. In other words, for any sheaf given as a point of this moduli space, we have that F is the push forward, is isomorphic to push forward of some module G, where G belongs to OY modules, category of OY modules. It's a coherent sheaf on Y. Okay, so this is that. Now, we are interested in torsion sheaf theory on this ambient variety X, on this variety, this dimension D minus 1, complex dimension of this is dimension D. This is equal to dimension D. That's dimension D minus 1, and that's dimension D. And so, in some sense, you have the moduli space of X, which is the moduli space of torsion sheaves on X, and this moduli space in this example is equal to the moduli space of OY modules G. So the two moduli spaces are isomorphic to each other. So I will not distinguish between the two, and I will just call them the same. I'm not saying that the G is torsion free on Y. G's could be supported on curves. But this is scheme theoretic support on Y basically tells you that if it is a sheaf support on a curve, it cannot deform outside of Y. Okay, so that's good, right? So you would essentially see that the moduli space I'm interested in is really the moduli space of the threefold. Okay? But now when you write down obstruction theories, the situation is different. So let's write down obstruction theories for m of x equal to m of y equal to n. On one hand, by the construction that I showed last time, starting with the Atiyah class, you will get r pi m over star of r hom f tilde shifted by d minus 1 to L dot of n. Why is it that we don't have any twisting? Really, it is because, you know, this is a Calabi-Yau and we don't have any twisting. The dualizing shift is also the canonical. And okay, so you have this thing. And on the other hand, you have phi of y, which is r pi m lower star of r hom, maybe r pi prime m, if you like. Actually, I can put it as r prime pi m. R hom g tilde shifted by d minus 2 goes to L dot of n. So really, this is the obstruction theory for L dot of mx. This is the obstruction theory for L dot of my. But these two are equal to each other, so I just call it L dot of m. Same with the tangent complex, right? And the maps here, this is x times the moduli space, and this gets mapped to m, and this gets mapped to x, pi of x, and inside here sits the y times the moduli space. This gets mapped to y, pi of y. This is the zero section of this guy, and you know, this also I call pi of m without losing generality. Okay, so this is that. Now, to make things easier, let me call this thing the complex E dot of x. Let me call this one the complex E dot of y. Okay? So this is actually one of those examples where you have a given moduli space, and for that moduli space, I am obtaining two obstruction theories. Okay, so first of all, you might want to know whether question is E dot of y or E dot of x equal to E dot of y? Are these two things the same? Or to know that, you need to do some analysis. So here is the argument. Point-wise, we can make a point-wise argument. Point-wise argument. We know that every sheaf is like push I lower star of G. So it's a push forward under the zero section of some sheaf G. So I can pull it back. So I can look at L R I upper star of I lower star of G. If I do that, I will get some sheaf G, and I will get an exact triangle where this thing gets tensored with conormal bundle or conormal sheaf of y inside x shifted by 1. Okay? This exact sequence is given by Bondal and Orlov in their paper. Okay? This is that exact sequence. In fact, this exact sequence is the exact triangle, sorry. This exact triangle is a split triangle. And y is cut out from x as a zero section of a bundle, and you can show that this exact triangle is a split. Since y is a divisor, conormal bundle of y inside x is just literally OY of minus 1. So nothing fancy here. Okay. So then, one thing I can do, I can apply Arham blank comma G to this exact triangle and see what I will get. If I do that, I will get Arham G comma G, then I will get Arham Li upper star, I lower star of G and G, and then I will get some Arham of G tensor with conormal bundle and comma G, but there is that shift by 1, so the shift will come out and become shifted by minus 1. Okay, so this is what you will get. Wow. So now, so you can use the adjointness property of drive, pull back, and push forward, and immediately identify this with Arham of push I lower star of G, I lower star of G. That you can do. And then by definition, these are F's. So this is nice because you have some exact triangle, which actually is a split, and it relates deformations of your torsion sheaf in X to deformation of the same sheaf in Y and the excess contributions. Okay. All right. So now, if you really look at the obstruction theory, with a little bit of shifting and so on, and pushing forward onto M, after applying R pi lower star, you realize that this guy induces for you E dot of X. And this guy, if you write everything in the family and push forward onto M, this guy induces for you E dot of Y. And then this guy is some term, which is the discrepancy term. So let me call this one D dot of Y in X. Okay, so what we get after writing in family and applying R pi M lower star, we obtain the following. We get E dot of X, the term in the middle, becomes isomorphic to E dot of Y plus D dot of Y inside X. The discrepancy. Okay? So what is this thing? This is the deformation obstruction complex of these sheaves F. This is the deformation obstruction complex of G tildes, and these are the discrepancies. Okay. Now, if you take homology, you will see that funny things can happen, right? So Ham GG goes to Ham FF, and this term vanishes. So in the Ham case, this thing vanishes. If you have Serre duality, for instance, for Calabi-Yau fourfold, X3 and so on also vanish actually there. However, there are always non-vanishing cohomologies contributed by this discrepancy term. And isn't this interesting? Basically, this is telling you that these two things are not equal to each other. You cannot show that they are equal to each other. Okay. Now, here is the theorem. We have the deformation obstruction complexes, but it's not enough to have these things to call them a deformation obstruction theory. We would like to have some object that understands deformations obstructions, but also a map from that object to the cotangent complex of the moduli space, and we would like to look at the maps and see how do they communicate. Then it becomes a So this is what we are going to do. We are going to look at these maps phi of mx, and this one I called it phi of x, and this one I called it phi of y. The two deformation obstruction theories. And we would like to know how are they actually communicating with each other. Okay? But also remember that the object that as a whole gives you the E dot of x together with the map to the cotangent complex is the Atiyah class. You remember that we used the Verdier duality? So all I need to do for these sheaves F tilde, I write the Atiyah class, universal truncated Atiyah class, and I write universal truncated Atiyah class for the G tildes, and I just compare Atiyah classes with each other and see what I get. Okay? So this is the theorem now that we had earlier last year. It's more or less, it was like an exercise. So the theorem is the following. You have this theorem. This is with Diaconescu and myself and Professor Yao. Here's the statement of the theorem. Consider universal relative truncated Atiyah class. Classes. First of that is the Atiyah class of x times m relative to x for this universal sheaf F tilde, which is a point inside this hom in the derived category of the F tilde derived tensor product with pi m upper star of L dot of m shifted by 1. The other one is the Atiyah class of y times m over y of this sheaf G, which belongs to hom in the derived category of x times m. This is hom in the derived category of y times m from G tilde, same thing as above. Of course, there is the truncated one always. Consider these two. Then the statement is the following. Then there exists a decomposition and R hom bounded x times m F tilde I m upper star of L dot of m shifted by 1 isomorphic to I times identity of m push forward R hom dB of y times m G tilde times I m upper star of L dot m plus I times identity of m lower star of R hom same thing G tilde tensor with pi m upper star, pi y upper star of the negative canonical bundle of y, and then positive canonical bundle of y tensor with L dot of m shifted by 1. This is our E dot. This is, this is the thing that after push forward gives us the E dot. And this is the thing that after push forward gives us the E dot. This is E dot of x. This essentially induces E dot of x. This induces E dot of y. And this guy induces this discrepancy term of y in x. But all of it is written in the level of the bounded derived category of x times n. Then I need to push it forward onto m, and then it induces the things I want. So this is nothing new. This is the statement that I put there. With respect to which a tier class of f tilde x times n relative to x factors through this term, factors through the second, the first one, factors through I times identity of m r hom g tilde pi m upper star L dot of m shifted by r. Okay. So what does this say? You have E dot of x. You know that it becomes E dot of y plus discrepancy term D dot of x. But when you compose with the map, you have the map to L dot of m here. And the idea is that this map, this guy, via this decomposition, factors through this term, but doesn't see this term. So it becomes this guy, and then this term will be giving us a 0. Okay? If normal bundle of y in x is negative. So in fact, if the statement is that if this is the if and only if, the statement is that if this guy is the case, then a tier class of f, relative a tier class of f becomes relative a tier class of g and 0. So it is, after all, true that even though you can obtain two obstruction theories for the same moduli space, if the bundle, normal bundle of y in x is negative, then you will only calculate one invariant. But remember, if it is not negative, since the derived category is blind with respect to the underlying geometry, you always get this extra term in here, this d dot term in here. And so you will calculate different invariants. Okay? Now, this theorem is general if you have the variety and if it has a divisor with a negative bundle, like a normal bundle is an ambient variety, we can always do this. So here our variety is given as a total space of a bundle. But essentially, because the exact triangle I just showed you, coming from Bondal and Orloff, is general, you can fix a linear system of divisors in your ambient variety and take an anti-ample linear system and then ask for sheaves supported on the members of the linear system, and you can repeat the argument. And so it's the same. It goes through. You can have different geometries too. You can have some other geometries as well. But it is funny, as soon as the normal bundle is not negative, then you cannot get this thing. For instance, if you have a surface vibration, like a K3 vibration, this is one of the examples Dennis and I talked about. You have a K3 vibration, K3 fiber 4-fold, and you have sheaves supported on the fibers, right? Then basically there is a 3-fold over there that you can distinguish, but that 3-fold doesn't have negative bundle. You can think of a K3 fiber 4-fold where the base of the vibration is a P1 times P1. And then you can look at the total space along one of the P1s. And that gives you a K3 fiber 3-fold sitting inside the K3 fiber 4-fold. But this analysis doesn't necessarily work. because this condition will not be satisfied. Okay. All right, so that is what we will prove. And so hence, as a corollary, then via the constructions, you can see that the virtual class of the moduli space obtained by E dot of x, if it exists, it's equal to the virtual class of the moduli space obtained by the divisor inside. So if you're interested in constructing the virtual cycle for the moduli space of coherent sheaves on a fourfold, in this case, you can take this as the definition. Often, what we have discussed in the derived geometry series is that we have a moduli space with shifted symplectic structure. This moduli space has -2 shifted symplectic structure. And so locally, you can write it as the critical locus of a function. But there has been less discussion on constructing its virtual cycle. But in this particular case, the moduli space is the isomorphic to the threefold moduli space, and looks like the deformation obstruction theories are also the same. The complexes are not the same, but the theories are the same. Okay, finally, some example. Here is an example. Let S be a smooth projective complex surface, a smooth projective complex surface with canonical of S numerically effective, okay, and D inside S an effective divisor. So then, out of this data, I can construct a threefold and a fourfold. So let X be the total space of this rank 2 bundle, K of S twisted by D plus OS twisted by minus D, together with the projection map onto S. So this is a fourfold. I call it X4. And then inside this fourfold sits this threefold, which is the total space of just K of SD with a map Q prime, let's say, onto the surface S. Okay. Okay. So this is what you have. Okay. All right. So as you can see, the fact that tensor product of these two line bundles is the canonical of S over this S guarantees that X4 is a Calabi of 4. And the fact that this guy has the normal bundle O of minus D actually guarantees that this satisfies the conditions of that theorem over there. Normal bundle of Y inside X4 is the term that you don't see in here, so this is this one. And we picked the divisor to be negative, so it's guaranteed that this guy is negative. All right, so we have this geometry. Now, we can look at moduli space of sheaves supported on the surface. So let M be H be the hyperplane bundle on the surface. Some nice amplification. Then I can look at moduli space of sheaves on X with the Chern character gamma, which is the set of sheaves in compactly supported coherent sheaves on X, where Chern character of my F is equal to 0, 0, 2, beta n.
In this case, Y, the threefold Y itself is also non-compact.
Yeah, also non-compact. Yeah.
Doesn't matter.
No. And this equal to the moduli space of sheaves on Y, F in coherent, compactly supported coherent sheaves on Y, where Chern character, I call these things G, and the Chern character of the G is the realization of the same chain character, but inside the threefold. Okay, and okay, yeah. So basically, then by the construction as a corollary, we can see that the Dalton-Thomas invariance of x4 with this chain character is equal to the Dalton-Thomas invariance of y3 with the chain character. And now, for instance, an example for such a situation is if S is an elliptically fibered K3 surface with fiber F, for instance, fiber divisor F, in which case I can take this effective divisor M times F for M very large. Okay, so if I do that, then that's it. I can then I can just compute. So partition function of this thing is something like this, and I can something like 0, 0, 2 beta n. Oh, but I want for the fiber class, for the curve class to be the class of the fiber, elliptic fiber. So here I would like my beta to be equal to fiber class, so this is my beta. If I calculate this thing, and if I define this thing as a sum over all dt of x to fn q to the n minus 2, so I'm adding over n, these are point-like instantons, then I can realize that here this is the result of calculation. We will get s minus 1 over 2 delta inverse of q to the 1/2 plus delta inverse of minus q to the 1/2 if m is even, and if m is odd, then we will get s inverse over 4 delta inverse of q squared. And here for us, delta of q is this discriminant hospital form. So it is 1 minus q to the n to the power 24. And what is s? You know, after proving that these invariants do match with the invariance of the threefold, because the threefold you asked, because this thing is also non-compact, we use localization to calculate the invariance. And so there is a torus that acts on the fibers of this line bundle on this one, and this is the equivariant parameter of that torus. So our partition function is written with respect to that equivariant parameter. And in fact, the way we define this thing is this belongs to q minus 2, some ring over the power series in q with rational coefficients and also coefficients in equivariant parameter s. Okay, so basically this is the end of the lecture today. And so there was an example, the motivation behind this was that there was an example in the recent paper of Malik and Saul and Toda where they have been looking at sheaves supported on surface. These are D4, D2, D0 branes, obviously, but they didn't have any thickening outside of the surface in general. Our sheaves in here do have thickening outside of the surface, but they thicken enough so that they don't have thickenings outside of the threefold. So they have set theoretic support on the surface, but skin theoretic support on the threefold. And so the threefold geometry is enough to describe it. So this is somewhat a mild generalization of what they did. Okay, so, and we didn't use any of the machinery of derived geometry, splitting of the obstruction bundle. We didn't do any of that. Of course, if you have sheets supported on the surface, which have thickenings outside of the support, even beyond the threefold, you can also calculate. You can also obtain. So maybe next time I actually talk about those things. I have that kind of thing too. I mean, it is not so hard actually. You can see what is going on, and that is also an interesting story. But I wanted to mention this as an exercise basically because sometimes you don't really need to go to the full fold. You know, if your geometry is not so. Okay, so we stop and we go to the